All right, welcome to chapter 4.1, the chain rule. Why do we need something called a chain rule? Well, let's look at a couple derivatives that we know how to do from chapter 3. We know that the rate of change with respect to x of sine of x is cosine of x. We also know that the rate of change with respect to x of x squared minus 4 is 2x. So we used our trig rule on the first one, we used our power rule and our derivative of a constant rule on the second one. But what is the derivative with respect to x of sine of x squared minus 4? This becomes a little bit more complex. What we're going to be doing is we're going to be talking about how to find this directly. So let's look at a quick example, a numeric example of this kind of problem. So if we know that the derivative of y with respect to x is 6, so that's something that has a slope of 6. And we know that the derivative of y with respect to some other function u is equal to 2, and the derivative of u with respect to x is 3. We could say, and now, notice that y is a function of u, so we've got y equals some function of u. We've got u is some function of x. And so then what's the relationship between y and x? We would say that the derivative of y with respect to x was the rate of change of y with respect to u times the rate of change of u with respect to x. Now, there is a temptation to say, oh, look, fractions, and start crossing things up. These are not really fractions. But let's think about this in terms of physical rate of change. So here, what we are saying is that y changes twice as fast as u. And here we are saying that u changes 3 times as fast as x. And therefore, y, that's a y, changes, and I'm going to run out of room to write here, 6 times as fast as x. And hopefully you can see the logic behind that statement, that if this is true, and if this is true, then therefore that must be true. So dy dx, the rate of change of y with respect to x, is equal to 2 times 3, which is 6. So if you're in my class, if you would go ahead and do exercise 1 in the book, that would be great. And you can pause the video and come back when you're done. Okay, so let's look at example 2. Example 2 says that y is equal to 3x squared plus 1 squared. And we're going to split this into a composite function. We're going to say that y is equal to u squared and u is equal to 3x squared plus 1. Well, the rate of change of y with respect to u is 2u. The rate of change of u with respect to x is 6x. So the rate of change of y with respect to x must be 2u dy du times 6x du dx, based on what we did on the previous page. But we also know that u is equal to 3x squared plus 1, which means that dy dx, the rate of change of y with respect to x, is twice that times 6x. And simplifying this, we get 12x times 3x squared plus 1, which is 36x cubed plus 12x. So now I want to show you how we know for a fact that this is right. Let's take the original equation, y equals 3x squared plus 1 squared, and let's multiply it out. This is the binomial squared, and so what we end up with here is we end up with 9x to the fourth plus 6x squared plus 1. And of course, using all of my rules from chapter 3, I can just use the power rule, bring down the 4. 9 times 4 is 36. Reduce the 4 by 1. Bring down the 2. 2 times 6 is 12. Reduce the power by 1. Derivative of 1 is 0 because it's a constant. And wow, this is exactly the same as what we got on the previous when we used our new idea of these composite functions. All right, so go ahead and do exercise 5. Again, if you're in my class or if you're just following along, these are the reason I give you these is because they're just a quick practice of what we just talked about. And I will make just a quick comment that this is actually easier than the composite rule or the composite rule on the previous page, but that's not always going to be true. I started with one that you could do both ways so that we could see how it worked. Because there's a lot that we just can't do another way. We don't have any way. If we had, I mean, if every function could be we could take the derivative of without using a chain rule, then why bother having a chain rule? So, all right, we'll be back with video 2. Thanks for watching.